Hello students, welcome to Sankalp Learning. This is Aishwarya Enkimat. Welcome to the second session of D and F block elements, where we are going to discuss the synopsis of D and F block elements. In the previous session, we have already discussed some of the important synopsis regarding D and F block. Now we are going to go further with the synopsis. So let us see which is the next point we are going to discuss. So here we are going to talk about the transition series 3D transition series. ಇದರಲ್ಲಿ ನಾವು ಏನು ಡಿಸ್ಕಸ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ ಇವತ್ತು ಫಸ್ಟ್ ಕಾನ್ಸೆಪ್ಟ್ ಯಾವ್ದು ಮಾಡ್ತಾ ಇದ್ದೀವಿ ಅಂತಂದ್ರೆ we are going to talk about the standard electrode potential SEP ಅಂತ ಅಂತೀವಿ. So let us discuss the first important synopsis, that is standard electrode potential. Now, what is standard electrode potential and how it is related to our transition elements, how it defines, what all we are going to discuss here. So standard electrode potential alli ನಾವು ಏನು ಡಿಸ್ಕಸ್ ಮಾಡ್ತೀವಿ. So let me write here standard electrode potential. This is the first concept in session 2, what we are going to discuss. Standard electrode potential, which is denoted as E naught. So standard electrode potential antandre enu, the standard electrode potential values, it depends upon the total enthalpy change. So total enthalpy change mele depend agutte. So what is this total enthalpy change? Total enthalpy change, the total enthalpy change which is involved during the reaction, enthalpy and namagottu, which is involved during the reaction. Yav reaction appa? During the formation of a metal ion, it is nothing but it is enthalpy of sublimation. Adanna navu hege baritivi? Delta S H. Delta H stands for enthalpy, S stands for sublimation. Enthalpy of sublimation plus ionization enthalpy plus enthalpy of hydration. Enthalpy of hydration. So what is this total enthalpy change? It is the sum of enthalpy of sublimation, enthalpy of ionization, ionization enthalpy athwa enthalpy of ionization anbodu, and enthalpy of hydration. So if the sum of these three terms, is less than the atomic number, is less than the enthalpy of hydration, if the sum of all these three terms, it is less than the enthalpy of hydration, then the total energy change will be negative. The total energy, let me repeat, if the sum of these three terms, or you can say, let me call it as x plus y plus z. ನಾನು ಏನಂತ ಡಿನೋಟ್ ಮಾಡಿದ್ದೀನಿ? X is nothing but enthalpy of sublimation, y is nothing but enthalpy of hydration, sorry, enthalpy of ionization ಅಥವಾ ನೀವು ionization enthalpy ಅನ್ಬೋದು, and delta H hyd is nothing but enthalpy of hydration. If the sum of x and y, is less than z, that is, if the sum of enthalpy of sublimation and ionization enthalpy is less than hydration enthalpy, then the total enthalpy change will be negative. So total enthalpy change negative adre, what does that mean? Negative means the reaction of formation of metal ion is exothermic. It is exothermic, and the metal ion will be more stable. So this is what we understand from this particular equation. So if the total enthalpy change is more negative, ion becomes still more stable. So such ions will have very low enthalpy of SEP antivi. So if the total enthalpy change is very, very negative, then ion becomes more stable, and such ions will have the lowest values of standard electrode potentials. Hey Kappa, how to explain this concept? How to explain this? Let me take an example. M plus 2 ion, which is going to form M ion. Couple reactions antivi now. When we talk about standard electrode potential here, electrochemistry chapter alli you nodirbodu. Yeah. So you can see here M plus 2 ion. This is the dipositive ion. When it takes 2 electrons, an equilibrium is established, you get metal ion M, neutral metal ion you get. The E naught for this value, standard electrode potential, E naught antandre enu? Standard electrode potential for this value, for this particular reaction, if it is low, what does that mean? If it is low, it means that the tendency of the metal ion to undergo reduction is less. Andre, this metal ion, this particular metal ion will act as the best reducing agent. It will act as the best reducing agent. Andre, it will help for reduction. It will help for reduction, but instead it will undergo oxidation. Andre reduction adu swanta reduction agalla. It will act as a reducing agent. It will help in reduction and itself undergo oxidation. You know the definition for reducing agent. ಏನಂತೀವಪ್ಪ? Reducing agent andre which helps in reduction and itself undergoes oxidation. So it will undergo oxidation very easily anta antivi. So from this we can conclude that we can say that lower the SRP value, standard reduction potential, adana hege baritivi? E naught anta baritivi. Lower the SRP value, more is the reducing power. Can we say that? More is the reducing power. So ಎಷ್ಟು ಕಡಿಮೆ SRP ವ್ಯಾಲ್ಯೂ ಇರುತ್ತೆ, more is the reducing power ಅಂತೀವಿ. So ಎಷ್ಟು ಕಡಿಮೆ ಅಪ್ಪ ಅಂದ್ರೆ ಏನು? You can take it as E naught value negative. If E naught value is negative, that means E naught value for a particular metal ion ad negative idre, what does that mean? It means that it is a better reducing agent. ಇದನ್ನ ನಾವು ಕಾನ್ಸೆಪ್ಟ್ ನ ಡಿ ಬ್ಲಾಕ್ ಎಲಿಮೆಂಟ್ಸ್ ಅಲ್ಲಿ ಹೇಗೆ ಅಪ್ಲೈ ಮಾಡೋದು? If you see 3D series, 3D series elements, scandium, titanium, vanadium, chromium, copper, all these elements, if you see along the 3D series, the standard reduction potential value goes on increasing. That means the negative values of electrode potential goes on decreasing. Antartha, hauda? So along the 3D series, the standard reduction potential values increases. The tendency of metal to undergo oxidation decreases. Antartha. Why? It is due to the sum of first and second terms, that is enthalpy of sublimation and enthalpy of hydration. Okay, so in general, when we talk about the standard reduction potential of transition metals, the standard reduction potentials of transition metal atoms, metal ions, but here there is an exception, except copper and mercury. The standard reduction potential except copper and mercury, yes, it is lower than that of hydrogen. It is lower than the standard reduction potential of hydrogen. Yes, thus transition elements with negative SRP, they have tendency to get oxidized. So transition metals ige negative SRP ide, they have negative standard reduction potential and they get oxidized very easily. They get oxidized. That means they act as reducing agents. So they get oxidized and liberate. They get oxidized and liberate hydrogen from dilute acids. Yes, this is very important. So transition metals, they have negative SRP. What does that mean? They get oxidized and liberate hydrogen from dilute acids. However, some metals like chromium, if you see chromium, they get protected. See, they get protected by the formation of their impervious layer itself. Yes, therefore, they form a layer of chromium oxide, Cr2O3 layer form agate. A metal mele, the layer gets formed when it reacts with oxygen. So, like how you see aluminium, adu bega corrosion agala antivi now. It is a protective corrosion antivi. Yakappa protective corrosion? Because aluminium reacts with oxygen and forms aluminium oxide, which forms a layer around the aluminium, and it will protect the things which are there, protect the element first, and the things which if you are coating something, like new aluminium foil use martira to pack your food and all. Why you use aluminum foil? Because it does not undergo corrosion antivi. Why it does not undergo corrosion? Because it forms a layer of aluminum oxide and that layer acts as a protective layer. Similarly, chromium also, it will react with oxygen and it forms an impervious layer of chromium oxide and therefore does not liberate hydrogen. It does not liberate hydrogen. This is the reason why chromium does not liberate hydrogen. In spite of their negative SRP values negative idru kuda, transition metals are not that good reducing agents. Like how you have S block elements, they are best reducing agents. Yes or no? We know that. We have studied this. S block elements are very best reducing agents. They are best reducing agents. Because they have got high heat of sublimation and high ionization energy. Comparatively to S block, the SRP values, though the SRP values of transition elements are negative, the S block D block elements are not that good reducing agents, we can say. Copper does not act as reducing agent itself. If you look at copper, copper, it does not act as reducing agent. Why? Do you know why? Because the standard reduction potential value of copper is positive. So copper is having positive SRP. Since copper is having positive SRP, it has lesser tendency to undergo oxidation. It has lesser tendency to undergo oxidation to form Cu plus 2 ion. The high energy required to transfer Cu to Cu plus 2 ion, the energy is very high, and that is compensated or balanced by hydration energy anta ಹೇಳ್ತೀವಿ ನಾವು. If you look at second element, one more element, Au, that is gold, it is having the highest positive value of SRP. Highest positive value. Therefore, this is also least reducing agent anta ಅನ್ಬೋದು. This is also least reducing agent. We should be knowing some of the important concepts here. Yes, zinc, Zn, it is having negative SRP. So negative SRP andre, it will act as good reducing agent. It will act as good reducing agent. Copper, as I said, does not act as reducing agent because its SRP value is standard reduction potential value is positive. From this electrode potential values, that is standard reduction potential values, it is confirmed that also Mn plus 3, Co plus 3, these are strong oxidizing agents. Strong oxidizing agents. Yakanta helbodu because they are having positive SRP. Yes or no? Then vanadium plus 2, chromium plus 2, they are strong reducing agents. From the SRP values, this is confirmed. Reducing agents. Similarly, we can take some of the examples also. We can take some of the examples like you have, let me consider Fe plus 3. Fe plus 3, if you see Fe plus 3 and Fe plus 2, this is ferric, this is ferrous, yes or no? Fe plus 3 ion acts as oxidizing agent, whereas Fe plus 2 acts as reducing agent. See the difference. Same ion, sorry, same element, but different ion. Fe plus 3 acts as oxidizing agent, Fe plus 2 acts as reducing agent. What we can confirm from here is more the positive value, more the positive SRP value of SRP value, strong is the oxidizing agent. Oxidizing agent. Strong is the oxidizing agent. More negative the SRP value. SRP value. Strong is the, it will be a strong reducing agent. So nimge exam alli SRP values kotbittu which is the better oxidizing, is it a better oxidizing or reducing ant kedre, we can say if the SRP value is positive, it becomes strong oxidizing agent. If it is negative, it becomes athwa if the SRP value goes on increasing, strong oxidizing agent agate. If the SRP value goes on decreasing, it becomes reducing agent. Athwa negative SRP values e kotbittu 4 options kottu arrange them in the decreasing order athwa increasing order of reducing agent andre this point can be used. So more positive value, if the particular metal ion is having SRP value more positive, it will be a very strong oxidizing agent or a very weak reducing agent anbodu. If the SRP value is more negative, then it will be a strong reducing agent. It will be a very strong reducing agent anta anbodu. Let me take another example here if you want to understand this standard reduction potential. Scandium, it is plus 3 state. If it gains 1 electron, it will form scandium plus 2. If you see this reaction, the electrode potential value is very low. What does that mean? It means that tendency of, what does that mean? It means tendency of Sc plus 3 to form Sc plus 2 is very low. ಯಾಕೆ ಹೇಳಿ ನೋಡೋಣ. The tendency electrode potential value low ಇದೆ ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು, tendency of scandium plus 3 ion to form scandium plus 2 is very low ಅಂತ ಹೇಳಿದ್ವಿ. ಯಾಕೆ, why it is very low? That means it will not form that easily ಅಂತ ಹೇಳಿದಾಗೆ. See, scandium atomic number 21, the configuration is argon 3d1 4s2. This is a configuration. Scandium plus 3 andaga, its configuration 3 electrons are lost. It will have a configuration of Ar. And you know that argon, a noble gas, having a stable configuration. So since it is having a very stable configuration, the loss of electron or a gain of electron to such metal ion is not possible. Yes or no? Therefore, you are going to give an electron here. Now this scandium plus 3 ion has to gain an electron. So if it has to gain an electron, it has to gain an electron very forcefully. Yakantandre, it is very stable here. So forcefully ನೀವು electron na ಹಾಕ್ತಿದ್ದೀರಿ to form scandium plus 2. ಅಂದ್ರೆ it will form Ar3D1. ಇದಾಗಬೇಕು. Therefore, I said the tendency of Sc plus 3, scandium plus 3 ion to form Sc plus 2 is very low. Therefore, E naught value is very low. So scandium has the configuration of argon. Tendency of Sc plus 3 to undergo reduction to Sc plus 2 is low. Therefore, its oxidation state is what? It's a stable oxidation state is plus 3. So low values of electrode potential is due to what? It is due to stable noble gas configuration. Stable noble gas configuration ಅಂತ ಹೇಳ್ಬೋದು. Let me take one more example to make it very clear, because here this concept becomes important. ಯಾವುದೇ question ಕೇಳಿದ್ರು solve ಮಾಡ್ಲಿಕ್ಕೆ ಬರಬೇಕು. Mn plus 3, you want to give it one electron to form Mn plus 2. Now let us have a look at it. Mn plus 3 andre, it will be Ar18 3D4. And here, plus by gaining one electron, it forms Ar3D5. So comparatively, higher standard electrode potential values indicate what it means. The tendency of Mn plus 2 plus 3 to form Mn plus 2 is very high. Yakandre, if it forms Mn plus 2, if Mn plus 3 ion gains one electron, and if it is going to form Mn plus 2, it means it will have the stable configuration again, because half-filled configuration and half-filled configuration is very stable due to two reasons, that is symmetry and exchange energy. Therefore, you can say here the formation of Mn plus from Mn plus 3, the formation of Mn plus 2 is very easy. It is very high, as after reduction, Mn attains the stable half-filled configuration. Take another example. Fe plus 3 to form, it will gain one electron and forms Fe plus 2. So here it is Ar8, Ar I'll write. Here it is 3D5. Here it is becoming 3D6. So it will have E naught value will be low. E naught value will be low because the tendency of Fe plus 3 to become Fe plus 2 is very low due to stable filled configuration. 6 ಆಗ್ಬೇಕಲ್ಲ. Therefore, only strong reducing agents like stannous chloride, SnCl2, can reduce Fe plus 3 to plus 2. Stannous chloride ಇದ್ರೆ ಮಾತ್ರ Fe plus 3 ಇಂದ Fe plus 2 ಮಾಡ್ಲಿಕ್ಕೆ ಸಾಧ್ಯ. ನಿಮಗೆ ಯಾವುದೋ ಒಂದು ಕಾಂಪೌಂಡ್ ಅಲ್ಲಿ Fe plus 3 ಇದೆ, you want to convert it to Fe plus 2, then it should be a very strong reducing agent. Then only it is possible. So lesser the value of standard reduction potential, lesser the value of standard reduction potential means what? More is the reducing power. More is the reducing power. That is about standard reduction potential. Okay, then the next important property, transition metals, they form, let us discuss some of the very important, again, they form colored complexes. Okay, they form colored complexes. There are many reasons why do they form colored complexes. Formation of colored compounds. Yeke colored compounds form agate. Most of the transition elements, they form colored compounds. If you see copper sulfate solution, copper is a transition element, right? Copper sulfate solution nodidaga, copper sulfate solution is blue in color. Getting? I hope you all know this. Copper sulfate solution, it is blue in color. Then if you look at a cobalt solution, cobalt chloride solution, cobalt chloride solution nodidre, it is red in color. Now, it is because of the transition element, metal which is present, copper, cobalt agirbodu. Why these compounds form color? Why these elements form colored compounds? Why transition elements form colored compounds? The color of the complexes is due to absorption of light energy due to dd transitions in partially filled d orbitals anta antivi. So what does that mean? The reason for the color, it is due to, first one, it is presence of unpaired electrons. Presence of unpaired electrons. Presence of unpaired electrons. This is the first reason. The second reason is splitting of degenerate. Splitting of degenerate d orbitals. Degenerate d orbitals ಅಂತಂದ್ರೆ ಏನು? Degenerate orbitals ಅಂತಂದ್ರೆ ಏನು? Degenerate orbitals ಅಂತಂದ್ರೆ the orbitals which belong to same subshell but with same energy. ಯಾವ ಆರ್ಬಿಟಲ್ಸ್ ಸೇಮ್ ಸಬ್ಶೆಲ್ ಇರ್ತಾರ, ದೇ ವಿಲ್ ಹ್ಯಾವ್ ಆಲ್ಮೋಸ್ಟ್ ಸೇಮ್ ಎನರ್ಜಿ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಡಿ ಆರ್ಬಿಟಲ್ ಅಲ್ಲಿ ಯು ಹ್ಯಾವ್ ಡಿ ಎಕ್ಸ್ ವೈ ಡಿ ವೈ ಝೆಡ್ 5 ಸಬ್ಶೆಲ್ಸ್ ಇದಾವೆ. ಎಸ್ ಆರ್ ಡಿ ಸಬ್ಶೆಲ್ ಅಲ್ಲಿ 5 ಡಿ ಆರ್ಬಿಟಲ್ಸ್ ಇದಾವೆ. ಎಸ್ ಆರ್ ನೋ? ಡಿ ಎಕ್ಸ್ ವೈ ಡಿ ವೈ ಝೆಡ್ ಡಿ ಝೆಡ್ ಎಕ್ಸ್ ಡಿ ಎಕ್ಸ್ ಸ್ಕ್ವೇರ್ ವೈ ಸ್ಕ್ವೇರ್ ಡಿ ಝೆಡ್ ಸ್ಕ್ವೇರ್. These are all called degenerate orbitals. S is not having any degenerate orbital. It is having only one orbital. P is having 3 degenerate orbitals. ಯಾವ್ಯಾವಪ್ಪ? px, py and pz. D is having 5 degenerate orbitals: dxy, dyz, dzx, dx square y square, and dz square. So these are degenerate orbitals. Degenerate orbitals anta andre ಏನು? The orbitals which have almost same energy. They possess same energy. So due to two reasons, that is presence of unpaired electrons and splitting of degenerate d orbitals into two sets, one with lower energy and another with higher energy. These are the two reasons why it forms colored complexes. So what is the explanation for it? Let us take the explanation here. So when we talk about explanation, degenerate d orbitals alli splitting agate. Because of the splitting, there is what is happening there here? Formation of colored complexes. Colored complexes. As we have discussed, the difference between the two energy levels is less. n-1d and ns or subshells nodidaga, the difference between these two energy levels is less. The energy required for dd transition, the energy required for dd transition is available in visible region. In visible region. So it is available in which region? Visible region. Visible region and then absorb region antiv now. So a particular light energy of definite wavelength is absorbed. So some wavelength gets absorbed, lambda is absorbed, and the remaining wavelengths are transmitted. Remaining are transmitted. So the wavelengths which are transmitted, they will show the color. Transmitted radiations exhibit color. Remaining wavelengths, they get transmitted. The transmitted light has color complementary to the absorbed light. That means if the absorbed light is red, then transmitted light is blue-green. If the absorbed light is blue, transmitted light is orange. If the absorbed light is green, transmitted light is purple. If the absorbed light is violet, transmitted light is yellow-green. Yellow-green. So, yav light wavelength absorb agate, some of the remaining wavelengths, they get transmitted. So transmitted light eniruttalla, transmitted wavelengths, they will show the color. Therefore, the color of the compound will be due to the radiations which are transmitted. So the transition metal ions which contain completely filled d subshells, for example, Zn+2 agirbodu, cadmium +2 agirbodu, mercurous ion Hg+2, mercuric ion, I'm sorry, then Cu+1 agirbodu, or completely filled subshells Sc+3, then titanium +4. These all appear colorless. These all appear colorless. Yak heli? Because there are no unpaired electrons. There are no unpaired electrons. Therefore, they will appear colorless. So, the reason for transition metal compounds to exhibit color, yenu reason? The reason is because of two reasons. One is presence of unpaired electrons, and second reason is due to splitting of degenerate d orbitals into two sets, one with lower energy and another with higher energy. So, lower energy, higher energy dd transition alli, so ಆಗ್ತಿರ್ಬೇಕಾದ್ರೆ it appears in the visible wavelength. The visible wavelength ಅಲ್ಲಿ ಆಗುತ್ತೆ. So because of that, what happens? Some of the radiations are, some of the wavelengths of the radiations are absorbed and remaining are transmitted. So the transmitted wavelengths, they show color, and here are some of the colors. Okay. Then when we talk about atomic volumes and density, atomic volume and density, both are related because you know formula for density is mass by volume. So atomic volume, D block elements, they have got high density antandre low volume because they are inversely proportional. Yes or no? And low atomic volume. Okay. Atomic volume kadme irute. So lower the volume than S and P block elements, that is because of poor screening effect of D electrons. Across the period, the atomic volume goes on decreasing. Across the period, atomic volume decreases due to increase in the nuclear charge because Z increases, nuclear charge, that is atomic number increases, and down the group density increase. Andre across the period density increase agutte, down the group kuda density increase agutte. Two highly dense elements, if you see, one is osmium, it is highly dense, 22.57 grams per cc, and one more is iridium, it is 22.61 grams per cc. So zinc is exceptional. It has large atomic volume, but lower density. Scandium, out of the D block elements, scandium is the lightest element out of D block. Okay. Lightest transition metal anta antinu. Scandium is the lightest transition metal. Osmium is the heaviest transition metal. Heaviest and even densest transition metal. Please do remember these points. Okay. Then coming to the next point, that is formation of complex compounds. Formation of complex compounds. This I'll just brief out here. We'll be discussing about this in coordination compounds also. These transition metals, they form coordination compounds or complex compounds with electron pair donor molecules. With what? With electron pair donor molecules. Those molecules which donate electron pair, they are called ligands. They are called what? Ligands. We'll study in detail about this also. They will form with donor molecules. Some of the examples are CuNH3 4 times SO4. Yes, this is one example. K4 FeCN6. So these are examples for complex compounds. The reason is here because of high positive charge of transition metals and smaller ionic radii. Because of this, the polarizing power of transition metals is nothing but it is positive charge divided by size, or you can say ionic radius. So as a result, high positive charge of transition metals, it enables transition metals to receive, they will receive electrons very easily. They will receive electrons donated by whom? They will receive the electrons donated by ligands very easily. Because of this reason, they will receive the electrons donated by ligands very easily. Okay, this is one reason. Second reason is availability of d orbitals. Availability of d orbitals. Availability of d orbitals. So here for bonding, the vacant d orbitals form hybrid orbitals with the S and P electrons and accommodate electrons donated by the ligands. So vacant d orbitals iro karanakke, they will take the electrons from the ligands and they can occupy them in their vacant d orbitals. So stability of these complexes, it increases with increase in atomic number. Andre left to right hodange hege atomic number increase agate, stability of these complex compounds also increases. The complexes of transition elements are more stable in higher oxidation state. Element the oxidation state hege jasti aguttalla, the transition complex compound formed by that particular element is more stable than the lower oxidation state. Bond formed between transition metal and ligand is what? Coordinate bond. Very important. The bond formed, it is neither ionic nor covalent. The bond formed between transition metal and ligand. in form agattala. It is purely coordinate bond. That means the electron pair is shared by one atom. It is taken by another atom, but it is mutually taken by both the atoms. Ereduku a particular pair of electrons available irutte anta artha. Yes, it will be given by one pair of electrons will be given by one atom. That is called ligand. But that will be shared by ligand also and by the metal atom also. We'll discuss this in detail when we are talking about coordination chemistry. Coming to the next important point, that is catalytic property. Very, very, very important property, because of which transition metals are having wide number of applications. Catalytic property. These transition metals, they act as, or their compounds, they act as very good catalysts. What is the reason? The reasons are again two reasons we have. The first one is again presence of vacant d orbitals. Presence of vacant d orbitals for pairing. Yes, vacant d orbitals. And the second reason is tendency of transition metals to exhibit variable oxidation states. See, transition metals, they're having vacant d orbitals. Nodi ನೀವು 3D scandium nodidre, if you see scandium 3D1, so it is having so many vacant d orbitals. Getting? So because of the vacant d orbitals, and second reason is tendency of transition metals to exhibit variable oxidation states. Mn can show +2, +3, +5, and +7. So variable oxidation states it can show. Therefore, they act as a better catalyst. A particular element catalyst and act agate, or even the compounds of those elements also act as catalysts. Let me show you some of the examples we have discussed in previous slides also. Iron, it is used as catalyst in manufacture of ammonia. Yav process heli? In the manufacture of ammonia by Haber's process, iron is used as a catalyst. Then you have nickel, it is acts as a catalyst for dehydrogenation of oils and fats. To get vanaspati, for the dehydrogenation, if nickel is not there, we use finely powdered nickel. Yes, for dehydrogenation of oils to form vanaspati. We use finely powdered nickel. Manufacture of H2SO4 by contact process. Which catalyst is being used? Vanadium pentoxide is used for manufacture of sulfuric acid. Manufacture of H2SO4 sulfuric acid by contact process. Okay. Then you have one more example, MnO2, manganese dioxide. It is used in the preparation of oxygen from KClO3. Then cobalt is used for decomposition of bleaching powder. So these are some of the applications. Even titanium chloride, it is used as Ziegler-Natta catalyst. Titanium chloride, yes, trichloride. It is used as a Ziegler-Natta catalyst. So here, catalytic property, the reason presence of vacant d orbitals and the tendency of transition metals to exhibit variable oxidation states. So that is the reason. Fine. Then coming to the next property, that is, so we have discussed these. So all the D block elements, they are metals, hard, malleable, ductile, except mercury, which is liquid. We have seen why it is. They are good conductors of heat and electricity. Elements of 1B group are most conductive in nature. Conductivity order, you can see Ag, Cu, the best conductor, that is silver. Then you have copper. You have studied this in previous classes also. Covalent and metallic bonding both exist in an atom of transition metals. The presence of partially filled d subshell favors covalent bonding and metallic bonding. So we have discussed all these points. Reducing power, we have seen standard reduction potential. Here it is standard oxidation potential copper. Why standard oxidation potential? Because copper SRP value is positive. So it helps in oxidation, right? Therefore standard oxidation potential baraste. So it is least reducing element. Positive is there, least reducing agent agi act madate. AU, we have seen it is also least reducing element. Yes, because of high value of standard reduction potential. The poor reducing capacity of transition metals is due to high heats of vaporization, high ionization potentials. We have discussed this, low heat of hydration of these ions, right? This is being discussed. Density, atomic volume of transition elements are low compared to S block elements. So comparatively, they will have high density, which is the highest. We have seen high densities for osmium, 22.57, as I said, and for iridium, it is 22.61. I said, if you look at the scandium is the lightest transition metal, and osmium is the heaviest transition metal, right? Then in all the groups, okay, melting and boiling points is already being discussed. The transition metals, they form complex compounds. Catalyte, we have discussed it. Why is the reason? High, smaller size of metal ions and high ionic charge. Adirinda yen gottagate namage? We understand the polarizing power. Yes or no? We understand the polarizing power. Polarizing power ಬಗ್ಗೆ ಗೊತ್ತಾಗುತ್ತೆ. So polarizing power ಇರೋದ್ರಿಂದ they will accept the electrons donated by the ligands very easily. Therefore, they form large number of complex compounds. Catalytic property, just now we saw it is because of presence of incompletely filled d orbitals and for the larger surface area, and to exhibit variable oxidation states. They are used as catalysts, and we have seen the examples. Now, formation of interstitial compounds. Interstitial compounds antandre, interstitial, what does this interstitial means? Transition metals, they have got certain empty spaces. ಅದಕ್ಕೆ ನಾವು voids ಅನ್ಬೋದು ಅಥವಾ interstitial sites ಅಂತೀವಿ. So the interstitial sites or voids are much large enough where they can hold some of the elements like carbon, hydrogen, nitrogen, boron, etc. can fit in them, resulting in the formation of interstitial compounds. Yes, the diameter of such voids is enough to accommodate the elements like carbon, hydrogen, nitrogen, and boron. So they are non-stoichiometric compounds. They do not have fixed formulae. The guest atom decreases the malleability and ductility. They are harder and less malleable and ductile. Yeah, because of the presence of this guest atom, yaudu carbon agirbodu, hydrogen agirbodu, nitrogen agirbodu, ಅಥವಾ boron agirbodu, it will be present in the interstitial site. Yes, so because of this guest atom at the interstitial site, it will decrease the malleability and the ductility, and also increase the hardness of the particular transition metal. So interstitial compounds of iron and carbon are quite hard and dense. Iron ಮತ್ತು carbon interstitial compound ನೋಡಿದ್ರೆ, they are quite hard and they are very dense. The occupation of interstices of metallic lattice by smaller atoms results in more close packed structures. Therefore, the density of the transition metals also increases. ಯಾವಾಗ ಅವು interstitial compounds ಆಗಿ ಫಾರ್ಮ್ ಆಗುತ್ತಲ್ಲ, the density ಏನಾಗುತ್ತೆ, ಜಾಸ್ತಿ ಆಗುತ್ತೆ. So we have this is about the interstitial compounds. Then alloy formation. What are alloys? So what do we mean by alloys here? So alloys ಅಂತಂದ್ರೆ ಏನು? We have discussed alloys ಬಗ್ಗೆ ನಮಗೆ ಗೊತ್ತು, lower classes ಅಲ್ಲಿ we have seen. So alloys are nothing but they are homogeneous mixtures. Alloys are the homogeneous mixtures of two or more metals, or a metal and a non-metal. It can be a metal and a non-metal. These transition metals, they form alloys. We have so many examples. Why do they form alloys? Since d block elements have nearly same atomic sizes ನೋಡಿದೀವಿ ನಾವು. Up to middle of the series, it will go on slowly decreasing, remains constant till the end, and at the end it increases. ಹೌದೇನಿಲ್ಲ? So d block elements are having almost nearly same, not exactly I'm saying, nearly same atomic size ಇರೋದ್ರಿಂದ they can easily take up the position of one another in the crystal lattices and cause alloy formation. The alloys which contain mercury, they are called amalgams. So alloy agodrinda, the chemical properties of the constituents are retained. Chemical properties change agalla, but the physical properties are improved appreciably. Okay, so alloys of copper, if you see, you have Cu plus Zn. This is called what? This is called brass. Then you have Cu plus Zn plus Sn. This is nothing but gunmetal. Then you have Cu plus Zn plus Ni. This is called German silver. Then you have Cu plus Sn. This is nothing but bronze. Yes, these are some of the examples of alloys of copper. Then you can see you have alloy of iron also. You have stainless steel, which is stainless steel, which is nothing but alloy of iron, nickel, chromium, and traces of carbon. Then you have Invar steel. Invar steel, that is nothing but steel plus nickel. Steel is prepared and some appreciable amounts of nickel is being added. Alnico, you have iron, nickel, cobalt. That is nothing but alnico, iron, nickel, cobalt. So these are all the alloys which are obtained from transition metals. Then coloring properties we have discussed. Transition metals, they show transition metals are colored metals, or the compounds are colored. Yes or no? So why the compounds are colored? We have seen it is because of presence of vacant d orbitals agirbodu, athava it is due to splitting of degenerate d orbitals into two energy levels, one with lower energy and another one is higher energy. So two sets are split agodrinda the energy difference between the two is less, so it is observed in visible region. Therefore, some of the wavelengths are absorbed and remaining wavelengths which are not absorbed are transmitted. So transmitted energy, transmitted eniruttala, that will exhibit the color. And we have seen the examples for colors also. Then you have the next property, and you can see here, they absorb in visible region exhibiting color. Okay, magnetic properties, very important. Generally, transition elements exhibit magnetic properties. Magnetic, which behave like magnet. So you have paramagnetic substances, you have diamagnetic substances, you have ferromagnetic substances also. Diamagnetic matadbidana. What is diamagnetic substance? It is slightly repelled by magnetic field. Andre, it will not attract the magnetic, it is not getting attracted by magnetic field. They are called diamagnetic substances. Then what are paramagnetic? They are attracted by the magnetic field. Due to what is the reason why some of the transition metal ions are repelled and why some of the transition metal ions are attracted? It is because of presence of unpaired electrons. Very, very, very important point. Because of the presence of unpaired electrons, they will show, transition metals will show, they will show the magnetic properties. They will exhibit the magnetic properties. So here, to understand the magnetic properties, we have the concept. See, magnetic property andaga, lesser transition metals generally contain one or more unpaired electrons, where in n-1d subshell. In n-1d subshell, due to these unpaired electrons, they behave as paramagnetic. So paramagnetic edukantiv now, if there are one or more unpaired electrons, one or more unpaired electrons. If there are one or more unpaired electrons, it will show paramagnetic nature. Diamagnetic antandre eno? Diamagnetic substances. There are no unpaired electrons, zero unpaired electrons. There are no unpaired electrons. They are diamagnetic. So this magnetic character, it is being measured, magnetic character of the transition elements, it is measured in terms of magnetic moment denoted as mu. So what is mu? Root of n into n plus 2. Bm. Bm antandre eno? It is Bohr magneton. Bohr magneton, the unit. What is mu? Mu is nothing but magnetic moment. See, magnetic moment, it is associated with orbital angular momentum and also with spin angular momentum. But transition metals, due to environmental influence, orbital angular momentum is cancelled. So, ಇಲ್ಲಿ work ಆಗೋದು magnetic moment ಯಾವುದು? Only spin angular magnetic moment work ಆಗುತ್ತೆ. So, if you consider one example, let me take one example here. Titanium plus 3. Titanium plus 3 has got how many unpaired electrons? It contains only one unpaired electron. It contains one unpaired electron because 4s ಒಳಗಿನ 2 electrons ಹೋಗುತ್ತೆ and 3d ಒಳಗಿಂದು 2ಅಲ್ಲಿ 1 electron ಹೋಗುತ್ತೆ. So plus 3, it will have only one unpaired electron. So you can calculate mu. So mu ಹೇಗೆ calculate ಮಾಡ್ತೀವಿ? Root of 1. N is nothing but number of unpaired electrons. 1 into 1 plus 1. 1 plus 2. So 2 plus 1 is 3. 3 into 1 is 3. So root of 3, its value is 1.73 Bohr magneton. So this is the magnetic moment shown by titanium. So it is paramagnetic and it shows the magnetic moment of 1.73. Vanadium plus 2. So vanadium plus 2, it is having 3 unpaired electrons. So N is equal to S to 3. Therefore, you can calculate mu root of 3 into 3 plus 2. 3 plus 2 is 5. 5 threes are 15. So root of 15 is nothing but 3.87 Bohr magneton. That is also paramagnetic with a magnetic moment of 3.87. So paramagnetism in any So here we have some of the compounds, important compounds of transition metals. That is, first one is potassium dichromate. So potassium dichromate, here if you see, this is manufactured from the ore which is called ferrochrome, or it is called chromate. That is FeO Cr2O3 or FeCr2O4 we write it as. Okay. What we need to understand here is in potassium dichromate, chromium is in +6 oxidation state. Hegappa chromium +6 oxidation state. So you can calculate, you know how to calculate the oxidation state. K2Cr2O7, potassium, it is +1 into there are 2 potassium atoms. Let me know the chromium. I'll take it as X into 2. Then oxygen plus, I'll write it here, plus oxygen is -2 into 7. Correct. So it is 2 plus 2x minus 14. So 2x is equal to 14 minus 2. 2x is equal to 7. So x is equal to 14 minus 2 is 12. And here 12 by 2. So here it is 6. So chromium exhibits oxidation state of +6. Preparation of a potassium dichromate, there are 2 steps. First, potassium dichromate is not directly prepared from the chromate ore. First, sodium chromate is being prepared. You can see here, sodium chromate is being prepared. Finely powdered chromite ore, it is mixed with soda ash. It is mixed with soda ash and quicklime. The mixture is roasted in reverberatory furnace. You obtain yellow mass. You obtain yellow or orange mass, we say. So you can see here, yellow or orange mass is obtained. That is nothing but sodium dichromate. First you get sodium chromate and then you get sodium dichromate. This sodium dichromate is being converted. Sodium chromate is converted into sodium dichromate, and that sodium dichromate is converted to potassium dichromate. So it follows 3 steps. So here, first step, what happens here? Finely powdered chromite ore, it is treated with soda ash and quicklime. There, the mixture is roasted in the reverberative furnace where you get yellow colored compound, yellow colored mass of sodium chromate. This sodium chromate is then converted. It is then converted, or you can say it is extracted with water. The filtrate contains sodium chromate. That filtrate, it is treated with NaOH and O2, and there it is converted to sodium dichromate. The sodium dichromate is finally treated with KCl to form potassium dichromate. So sodium dichromate, why it is converted using KCl? Because sodium dichromate is more soluble than potassium dichromate. And chromates and dichromates are interconvertible in aqueous solutions depending upon the solutions. Okay. Then you have potassium permanganate. Potassium permanganate is nothing but KMnO4. In KMnO4, Mn, what is the oxidation? Can you tell the oxidation state of Mn here? The oxidation, let us see what is the oxidation state of Mn. So potassium is +1 into 1 plus Mn, we don't know the oxidation state, into there is 1 atom plus oxygen -2 into 4. Correct? So 1 plus x minus 8. So x is equal to 8 minus 1. So what is the value of x? It is +7. So Mn in potassium permanganate, it exhibits the oxidation state of +7. And how it is being prepared? It is prepared from pyrolusite ore. It is being prepared from pyrolusite ore, which is nothing but MnO2. So conversion of pyrolusite ore into potassium manganate, K2MnO4, it is being converted, and then it is being converted into permanganate. Manganate ion na now permanganate ion ke convert martivi. Yes. So how it is being converted? You can look at the reaction here, and we know it very easily. So commercial preparation, MnO2, it is fused with it is fused with KOH, then oxidized with air or KNO3, you get manganate ion. The manganate ion is subjected for electrolytic oxidation in alkaline medium. You get potassium permanganate ion. Yes. So potassium permanganate ion, it acts as a very strong oxidizing agent. It acts as a very strong oxidizing agent. In presence of dilute H2SO4, KMnO4 is reduced to manganese ion. MnO4, you can look at the ionic equation. So these are some of the important properties of KMnO4. What are the properties of KMnO4? So here physical properties of KMnO4 matadidaga, KMnO4 crystallizes as dark purple crystals with greenish luster, and its melting point is 523 Kelvin. It is soluble in water, 523 Kelvin. Chemical properties nodidaga, action of heat is stable at room temperature, but at high temperatures, it will decompose to give O2. At high temperatures, normal temperature, it is stable, but at high temperature, it decomposes to give O2. It decomposes to give O2. Then, if you look at the oxidizing nature, it acts as a strong oxidizing agent and notice here. If you look at the oxidizing action, KMnO4 acts as a very strong oxidizing agent in neutral solutions, acidic solutions, and even in alkaline medium. The oxidizing character of KMnO4, or to be more specific, MnO4 minus ion, manganate ion, the oxidizing character of manganate ion, it is indicated by high reduction potential value. SCP, it is very high. Andre acidic medium alli, let me show you. If you look at the acidic medium, alli, so here we have, if you look in acidic medium, so which is our ion? It is MnO4 minus. So it will take H plus ions, acidic medium electrons. This is in equilibrium. It will form Mn plus 2 plus H2O. E0 value here, it is 1.51 V. Yes. So you can balance this reaction. 8H2, 8. Here I'll take it as 5. And here it is 4. This is in acidic medium. In alkaline medium, if you see, it acts as oxidizing agent in all the three mediums. Alkaline medium, MnO4 minus plus 2H2O. I'll write the balanced equation itself. Electrons, 3 electrons, MnO2 plus OH minus 4 atoms, 4 OH minus ions. E0 value is 1.23 electron volt. So this is the ionic equation in acidic and alkaline medium for potassium permanganate. So in presence of excess of reducing agent in acidic medium, permanganate ion gets reduced to manganese ion. It gets reduced to manganese ion. In acidic medium, KMNO4 oxidizes KMNO4. These are some of the applications of KMNO4. It oxidizes ferrous salts to ferric salts. Okay, then it oxidizes oxalic acid. You know the equations also for this, to carbon dioxide. It oxidizes sulfites to sulfates, iodides to iodine. So these are some of the applications of KMNO4. Even you can look potassium dichromate ಬಗ್ಗೆ ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ. So here let me write K2Cr2O7. This potassium dichromate, this also has a good oxidizing nature. So this will also oxidize ferrous salts to ferric salts, oxidizes ferrous salts to ferric salts, and then even iodides to iodine also. Potassium dichromate also has got a better oxidizing agent. So this is about the applications of two important compounds in D block elements. One is potassium permanganate and another one is potassium dichromate. So to acidify KMNO4, only H2SO4 is used. HCl or HNO3 is not used. Why? Because HCl reacts with KMNO4 to produce Cl2 gas. But here we want O2. In alkaline medium, I have shown you the reaction. Alkaline or neutral KMNO4 solution oxidizes, we have said, iodides is being oxidized. What are the applications? In laboratory, it is used for manufacture, preparation of chlorine. KMNO4 is used as an oxidizing agent, as a disinfectant. It is used in making Bayer's reagent. Yes, so this is all about D block elements. So next we have, that is F block elements, which are called inner transition elements, which we will be taking up in the next session. This will be discussed in the next session. So before that, let us see all the properties which we have confronted here. Formation of the transition metals. So formation general properties, we have discussed about transition elements: from stable complexes, high melting and boiling points, from compounds which are often paramagnetic, they are hard, they possess high densities, they form compounds with profound catalytic activity, they show variable oxidation states, they form colored ions. So these are all the things what we have discussed. One more point I just missed out to talk about is, if in case of the examples which we took, that is the KMNO4 ಆಗಿರಬಹುದು ಅಥವಾ K2Cr2O7 ಆಗಿರಬಹುದು. These two examples here, what you see, chromate K2Cr2O7 ಅಲ್ಲಿ potassium dichromate ion structure will be asked. One chromate ion. So chromate ion has how many oxygens? CrO4. This is chromate ion. CrO4 minus 2. Dichromate ion andre Cr2O7 minus 2. So chromate ion structure nodidre, this will be asked. Cr. So here we have oxygen, and this is minus 2. This is chromate ion. It is having what structure? It is having tetrahedral structure. This is asked question frequently. Multiple questions ali this is asked. Dichromate structure, if you look, so dichromate ion, there is involvement of this bridge in dichromate ion. Hegeppa? Cr. So these three oxygens, they are bonded like this. Yes, then here one oxygen forms bridge between two chromium atoms, and here you have the remaining three and the charge with minus 2. So if you look at this bond length, it is 180 picometers, and here the bond angle CrOCr bond angle is 131 degrees, and CRO, this bond length, if you see, this is 180 and this is 161 picometers. See, look at the bond length difference. Bridging bond length and the other bonds, CRO bonds are 161. This is also 161. This is also 161 picometers, 161 picometers. Here also the three bonds, 161, 161, 161. But the bridged bonds, it is 180, 180 picometers. Yeah. Then if you look at Maton yav discuss madidvi, we discussed about potassium permanganate, KMNO4. If you look here, manganate ion, potassium permanganate ion, MnO4 minus. Here, if you see, the structure is Mn double bonded to oxygen, double bonded to oxygen, double bonded to oxygen, and one is single bond with -1 charge. So Mn here it is in +7 oxidation state, and it is having sp3 hybridization. It is having sp3 hybridization. So it is used as oxidizing agent. It is used as a disinfectant against various disease-causing germs. It is used for sterilizing wells of drinking water. Dilute alkaline KMNO4 solution. Just now we saw dilute alkaline KMNO4 solution. KMNO4 solution is known as Bayer's reagent. It is known as Bayer's reagent. So this is about alkaline KMNO4 and the previous slide, that is K2Cr2O7. Where is this K2Cr2O7 used? K2Cr2O7, it is used as oxidizing agent. Then it is used in chrome tanning. Tanning industries only. For chrome tanning, this K2Cr2O7 is used. It is used as raw material for preparation of large number of chromium compounds. Bahಳಷ್ಟು chromium compounds manufacture ಅಲ್ಲಿ K2Cr2O7 is used as a large raw material, and it is primary standard. It is a primary standard in volumetric analysis. So this is the brief synopsis of D block elements. In the next session, we'll be discussing about the synopsis regarding F block elements. F block elements synopsis we'll discuss. I hope all the synopses are being cleared. There is no doubts regarding it, which will help us to solve most of the questions. Thank you.